In a nutshell, thermal physics is the study of heat. Heat energy, or thermal energy, is the energy of a substance or system in terms of the motion or vibrations of its molecules. The faster the molecules in a substance move, the more heat energy they have. If you wanted to know how much thermal energy there was in a glass of water, you would have to total up the energy of all the molecules inside it. Not only is this difficult to do, it isn't entirely helpful. A large glass of cold water has more heat energy than a small glass of cold water, but they feel just as cold. Because of this, we introduce a related term, temperature, which is the average kinetic energy of the molecules in a substance. A large and small glass of water might have the same temperature, even though the large glass of water contains more overall heat energy. Heat can also transfer, so thermal physics talks about this as well. Touch a metal chair leg and it feels colder than a wooden desk. But if they're in the same room and have been there for a while, it's likely that they actually have the same temperature. That's because your hands don't measure temperature. They measure heat transfer, and metals conduct heat particularly fast. The heat in your hand is lost quicker when you touch the metal chair leg, even though the chair leg has the same temperature as the desk. But that's conduction, just one of the types of heat transfer that is studied in thermal physics. When you begin to study these molecular motions in depth, the topic quickly balloons into a wide variety of areas. So next, we're going to talk about the general areas that collectively make up thermal physics. The key areas of thermal physics we're going to talk about are thermodynamics, statistical mechanics, and kinetic theory. Thermodynamics is the study of the movement of heat energy. This encompasses the laws of thermodynamics, which talk about how and why heat moves, the types of heat transfer, conduction, convection, and radiation, phase or state changes, and the relationship between energy and work. Studying thermodynamics also means talking about heat engines, how we can extract useful work using a combination of cold and hot reservoirs. Kinetic theory is a simplified description of gases that describes how the molecules move and react to situations, predicting what will happen to the gas as a whole. Or in other words, it uses simple physical laws for the molecules that make up the gas to explain the way gases behave on everyday scales. Kinetic theory also defines terms like temperature, the average kinetic energy of gas molecules, pressure, the force exerted by the gas molecules on the walls of their container, and volume, the space the gas molecules take up. Kinetic theory not only defines these properties, but also their viscosity and thermal conductivity, all using the composition and motion of the molecules. Last of all, statistical mechanics takes kinetic theory a step further. It uses statistical probabilities to predict the likely behavior of the molecules in a system. Statistical mechanics rejects terms like temperature, pressure, and volume, and shows how they arise from the statistical behavior of molecules. It's more powerful than kinetic theory, but also correspondingly more complex. In AP Physics, we'll be focusing mostly on the first two topics, discussing many of the topics only mentioned in this lesson in much more detail. Thermal physics is the study of heat. Heat energy, or thermal energy, is the energy of a substance or system in terms of the motion or vibration of its molecules. The faster the molecules in a substance move, the more heat energy they have. Temperature is the average kinetic energy of the molecules in a substance. A large and small glass of water might have the same temperature, even though the large glass contains more overall heat energy. Thermal physics encompasses thermodynamics, statistical mechanics, and kinetic theory. Thermodynamics is the study of the movement of heat energy. Kinetic theory is a simplified description of gases that describes how molecules move and react to situations, predicting what will happen to the gas as a whole, and statistical mechanics uses statistical probabilities to predict the likely behavior of the molecules in a system. Statistical mechanics rejects terms like temperature, pressure, and volume, which are used in kinetic theory, and shows how they arise from the statistical behavior of molecules. It's more powerful than kinetic theory, but also more complex.